condition is become true. Okay, so if the while condition become true, we have seen in the mutex. Okay, in the mutex we have seen that if the condition true, then mutex block in the mutex it block itself, and after some time it can be awake by the current process. So similar kind of technique we can implement here also. So semaphore also can be a blocking. That means it also can be blocked itself if the condition in the while loop become true, or it can be continuously executing in the while loop like the spin lock for the status of the uh, variable. So that is nothing but the non-blocking. So if yes is that is semaphore variable, if it is initially set to 1, then in the blocking semaphore it is similar to a mutex. If it is a 1, then it is similar to a mutex. And for the non-blocking semaphore, if it is set to 1, then in the non-blocking semaphore it is similar to a spin lock. Okay, so that will be the case. So there are two types of semaphore. One is the binary semaphore and second is the counting semaphore. Definitely for the binary semaphore, there will be only two values, that is 0 and 1. Two values only for the binary semaphore. Whereas the counting semaphore, the value will be greater than 0. That is the 0, 1, 2, 3. That is up to some certain limit. The value of the semaphore you can define. That is the counting semaphore. Generally, the binary semaphore, it is implemented when there is a single instance of resources is present. Whereas the counting semaphore, it is implemented if there are multiple instances of the resource is present. Okay, for example, we can consider the example of printer. If there is only one printer, then we can use binary semaphore. But if suppose there are 4 to 5 printer are there, then in that case we can use the counting semaphore. So in that case, if there are 5 printer, then you can initialize the count of the semaphore, that is maximum up to 5. Okay, so if there are single instance, implement binary semaphore. If there are multiple instances are there, then we can implement the counting semaphore. Okay. So this is the mutual exclusion implementation with the semaphore. Okay, so in the semaphore, we are using two functions, that is wait and signal. So in the wait function, it is performing the decrement operation. That is semaphore variable is decremented. So here I am using the variable mutex, and in the wait, the value of the mutex will be decremented. And afterwards, when after executing in the critical section, after successfully execute the critical section, it will perform the signal operation in which the value of the mutex variable will be incremented. So definitely in such case, the value of the mutex you can consider initially as a 1, so that in the wait operation it will be decremented by 1, so it will become 0, and again in the signal operation from the 0 it will become 1. Okay, so these two operations it is performed, and after that it will go to the remainder section, and then the looping will be continued. Okay, we can see this with our producer consumer problem. Okay, so this is the code. This is the producer consumer code with the semaphore. So the buffer size, it is n using a count variable as well as the two variable, that is the full and empty. Okay, we are using this 3 variables. So first while loop, it will check the true condition. Process will enter into the loop, and it will call the function produce item, and after the calling function, it will go for the wait operation. Okay, it will go for the wait operation. after performing wait operation, definitely here in the wait operation, first it will perform the wait operation on empty variable, where the value of empty it is set to n. Okay, first look at the initialization, that is full equal to 0. Okay, full equal to 0, that means there is no item in the buffer, buffer is empty, and empty variable it is set as the n. That is, if there are 5 buffers, then the 5 empty blocks are there. Getting full, it is 0, 0 blocks are full, and empty, it is n. Suppose there are 5 blocks, then empty blocks are 5. So since it is empty, so first process arrive, it will produce an item, then it will perform wait operation on empty. So value of empty it will decrement by 1. Then it will again perform the wait operation on mutex. So value of the mutex it will be a 0. Okay, since the value of mutex is 1, consider it as the 1, it becomes 0, and after that it is going to insert item into the buffer. It is going to insert item into the buffer, and after that it is performing the operation signal, and then afterwards it will perform the operation signal on full. So signal on mutex value from 0 to 1, and signal on full value from 0 to 1. Also it can be 1 to 2 and so on. Similarly, in the consumer, it will first perform operation on the wait. Okay, wait, and it will check the value for full. Then afterwards it will perform wait operation on mutex, and then it will remove the item. Okay, so see carefully here, during the producer item, producer without performing any wait operation, it is producing. Okay, it is producing because it is outside the buffer, so it is producing. So, but while inserting into the buffer, it is performing all the operation, wait and see. It is performing wait operation before entering into the buffer. But for the consumer, it can be retrieved after accessing to the buffer. So first is access to the buffer. So for that purpose, it have to first perform the wait operation. So it will first perform wait on the full, then wait on the mutex, and after that, if both waits perform successfully, then it will remove the item. And after removing, immediately it will perform the signal operation. It will perform the signal operation, and then afterwards it will consume the item. Okay, so likewise you can perform the we can provide the solution for the producer and consumer problem of the using the semaphore. Is there any confusion? Any confusion? Okay, in the book you have only this much code. Okay, this is the simple code for the given. So write down this code, this algorithm, since it is not available in your book. And it may be possible that in the notes also there might be some different, some minor changes may be there, because there are different variants present for solving this producer consumer problem. But we are checking only with perspective of our syllabus. Okay, so there may be some minor changes in the notes or in book as well as in my code, since the version may be different. Okay, so you can consider that point. So write down this code. I will give 2 minutes. Okay, finish. Okay, so any problem in producer consumer? Okay. The second classical problem is the readers and writers problem. Okay, so this is the second classical problem of synchronization. So in the readers writers problem, you can better understand with respect to the database. Okay, so in the case of reader, okay, if suppose uh, readers and writers problem, if readers are going to read the data, then in that case multiple readers can be allowed to access the data in read mode. Okay, so for the reader purpose, multiple sharing of the data, it is possible only in read mode. There should not be any updation. Similarly, if in the writer's case, if writing want to perform, then in that case only one writer is allowed. Only one writer is allowed in the critical section at a time. And I'm here calling it as the critical section. That is nothing but your shared data. So sharing, it is possible if there is a reading, but it is not possible in case of writing. If somebody is writing on the shared data, then definitely it should be a mutually exclusive. So for the writing case, it should be a mutually exclusive. That means only one writer is allowed to write something at a time. And if the task of that writer is over, then another writer can be allowed. So in the two cases, for the reader case, multiple data, it can be accessible by multiple processes. Same data or the shared data, it can be accessed by the multiple process for the reading mode, but for the writing mode, only one one writer is permitted to perform the operation on a shared data. Okay, so that is the problem, and this problem can be solved by using the semaphore. So two variables we are using in this case, one is the mutex and second is the write semaphore variable, and one more variable we are using, that is the read count. So the structure of a write process, that is given here first. So in the write process, our general structure of the semaphore we can implement. That is, we can perform wait operation on the write semaphore variable, then perform the writing on that writing in the critical section or writing on that shared data, and after that perform the signal operation. Okay, in the writer process, since only one process is allowed to enter into the critical section, or only one writer is allowed to write on the shared data, so that we can, okay, so for this purpose we can use the wait and signal function. So in the wait function, we are decrementing a write variable, and then user can enter into the section, and after performing writing, it can perform the signal operation, which is indicate to other process that they can access this updated data. So this is the simple structure for the writer process. Okay, this is the structure of the reader process. Okay, now this in the reader case, we should allow different processes or multiple processes to access the shared data, same data. So in that case, it is using the mutex variable, mutex as well as write. So in the first, it will perform wait operation on the mutex variable. After that, it will increment the read count. Then it will check if the read count is 1, then it will perform wait operation on write variable. Afterwards, it will perform the signal operation on mutex, and after that it is going to perform reading operation. After the reading, again it will perform mutex, wait on mutex, then read count will be decrement. If the read count is 0, again it will perform the signal operation on write mode, and then it will perform signal operation on mutex. Anything understood? काही समजले? Yes or no? As expected. See, एखादा रीडर जर रीड करत असेल, ओके, आपण काय म्हणलं की रीड करत असताना मल्टिपल युजर दे कॅन अलाउड. ओके, सिंपल सॉफ्ट कॉपी आहे, ती सॉफ्ट कॉपी 10 जणांना जरी प्रोव्हाइड केली तरी त्या 10 जणांनी पण ते रीड करू शकतात. ओके, पण रायटिंग मध्ये तसं होत नाही. रायटिंग एक जण राईट करत असेल तर बाकी सगळ्यांनी थांबायला पाहिजे. ज्यावेळेस त्याचं रायटिंग कम्प्लीट होईल मग त्यानंतर बाकीचे राईट करू शकतात. म्हणजे रायटिंग ओनली ॲट अ टाइम, but reading it can be possible by multiple user at the same time. That is one case. Second case, when reading is performed, writing should not be there. Are you getting? When someone is performing the reading, then others should not write on that. So for that perspective, they are using here signal and wait operation. आपली कंडिशन काय की रीड करताना डेफिनेटली सगळ्यांनी, समजा 10 इन्स्टन्स तर 10 जणांनी रीड करता आलं पाहिजे, पण ते रीड करत असताना बाकी कोणी राईट पण नाही केलं पाहिजे. ओके, जर सपोज राईट करत असेल तर त्या केसमध्ये त्याला आधी राईट करू द्यायला पाहिजे. रायटिंग परफॉर्म कम्प्लीट झाल्यानंतर देन ऑल अदर कॅन रीड. ओके, सो for the writing purpose also there should not be for the reading purpose also there should not be writing by others. So here it is considering both cases. So in the first wait operation, this wait of mutex, it is for the read count मला इन्क्रीमेंट करायचं आहे. रीड काउंट इन्क्रीमेंट करायचं आहे, तर त्यासाठी रीड काउंटला फक्त एकाचाच ऍक्सेस ॲट अ टाइम पाहिजे. त्यामुळे मी पहिल्यांदा वेटमध्ये म्युटेक्स व्हेरिएबल घेतोय, त्याचा रीड काउंट इन्क्रीमेंट करतोय. आता ह्या केसमध्ये पण म्युटेक्सचा काय असतं फायदा की म्युटेक्समध्ये फक्त एक जण ऑपरेशन करेल, बाकी सगळे शांत राहतील. ओके, म्युटेक्समध्ये काय होईल, फक्त एक जण ऑपरेशन करेल, बाकी सगळे शांत राहतील. मग ह्या केसमध्ये रीडर जरी असेल तरी त्याला रीड काउंट इन्क्रीमेंट करताना एकानंच फक्त करायला पाहिजे. असं नाही होत की बाबा रीड काउंटचं व्हेरिएबल ॲट अ टाइम दोघं तिघ जण इन्क्रीमेंट करतात. इट इज नॉट पॉसिबल. सो फॉर द इन्क्रीमेंटिंग द रीड काउंट ओनली one process should be present. So for that purpose, in the wait, mutex variable will be decremented. So from the 1, the value becomes 0. Since the value becomes 0, no other process can enter for the read count, for incrementing or decrementing the read count. So since wait operation perform, it will increment the read count. Suppose this is first process, so count was 0. So after the performing read count, it becomes 1. Now if read count 1, then perform wait operation on write mutex. Write mutex variable, write semaphore variable आहे. The write semaphore variable, it should be decremented. Now when this write variable decrement, that means no one other can perform the write operation. बाकी कोणाला write operation perform करता नाही आलं पाहिजे. सेकंड थिंग, एकानं जरी राईट डिक्रीमेंट केलं, एकानं जरी राईट ऑपरेशनवर वेट फंक्शन परफॉर्म केलं, राईट व्हेरिएबलवर वेट परफॉर्म केलं, तर त्या केसमध्ये अदर व्हेरिएबलला ते करायची गरज नाहीये. म्हणजे समजा सेकंड प्रोसेस आली रिडिंगसाठी, तर त्या प्रोसेसला परत हे वेट आणि राईट करायची गरज नाहीये, कारण ऑलरेडी ते एका प्रोसेसने केले. म्हणजे 10 प्रोसेस असतील आणि एका जरी प्रोसेसनी सांगितलं की कोणीही राईट परफॉर्म करू शकत नाही, तर त्या केसमध्ये that is sufficient so that in this case the wait is performed by right when read count is 1. जेव्हा पहिली प्रोसेस असेल, एकदा का पहिल्या प्रोसेसनं ते वेट ऑपरेशन परफॉर्म केलं तर बाकीच्या प्रोसेसला करायची गरज नाही, फक्त एकदाच ते प्रोसेस एकदाच ऑपरेशन करायची गरज राहते. सो आफ्टर परफॉर्म दिस वेट ऑपरेशन on the right semaphore variable, no other process can perform writing. So after that it is perform signal operation on mutex. So mutex it will be incremented to 1 so that the read count becomes free, so other process can enter for the read count and then it can perform the reading. Okay, after the signaling this mutex, after incrementing this mutex, it can perform the reading. Then after reading it can perform wait operation on mutex. Why? Because it wants to decrement the read count. It will perform the wait. Now after read count decrement, it will check the count of read count. If the read count is 0, that means there is no process to read the data. Then in that case, it can perform signal operation on write semaphore variable, on write variable, so that any other variable can write into that data. And then it will perform the signal on mutex. So two cases, one is the for the read count variable and second for the writing purpose. Okay, so for this two purpose, for this two condition, we have used two semaphore variable in reader process. Okay, so in short, again I am going to repeat it. So in the reader mode, first thing is multiple reader should perform the operation, only reading, and write operation should be restricted. So for to achieve both two functions or both two requirement, we need a two variable. One is the mutex, second is the write. Then for the read count, it will perform mutex operation. It will perform wait operation on mutex variable. So in the mutex, on the performing wait, it will increment the count. If the count is 1, then it will perform wait operation on write variable. So other process are restricted for the writing. Then it will perform signal operation on mutex so that other process can enter for the reading. And after that, it is going to perform reading operation. After reading, it want to decrement count. So again, it will perform wait operation on mutex, decrement the read count. Then it will check the condition. If read count is 0, if it is not 0, it will directly perform signal mutex. Otherwise, if its read count is 0, then it will perform signal write, and after that signal on mutex. Is it clear now? Is there any confusion or should I repeat? Okay, Ankita got clear. Other? Clear, or is still there any confusion? Okay, if there is no confusion, then write down the structure of the write process as well as read process. Okay, take your time. Okay, so finish. Okay, another classical problem of the synchronization is the dining philosopher problem. Okay, this is the popular problem. I think the solution of this problem is using in the Ethernet. Yeah, if I remember. Yeah, okay. Okay, so this is the dining philosopher problem. So first understanding the scenario. What is dining philosopher problem? So there are five philosophers as you can see in the diagram. These five philosophers sitting around the circular table. There are five plates. There are five plates as well as five chopsticks are there to read the food that is provided in the plate. And to eat this food or to eating, a philosopher needs to hold both the chopstick, or you can say both the fork. So for a philosopher, it needs both forks, both chopsticks, that is one on his left and one on his right. And if philosopher is not eating, then he is in thinking state. Okay. So scenario: five philosophers on the circular table, five plates are there, five chopsticks are there, and when the philosopher feels hungry, he should eat by using both chopsticks. One is on his left and one is on his right. Now, what is the problem statement? You have to develop an algorithm where no philosopher should be starved. If we consider the scenario that if suppose P1 is hungry, then he will take the chopstick 1 and 2. Since the chopstick 2 is taken by P1, P2 cannot uh, P2 cannot eating because it requires 2 and 3 chopstick, chopstick number 2 as well as chopstick number 3. But 2 is allocated to the P1. So P2 it will in where it will be in P3. If suppose P3 wants to eat, it will take third and fourth chopstick which is available. So it will start eating. P4, since P4 is not available, since fourth chopstick is not available, so P4 it will go into thinking state. And P5, chopstick 5 is available, but chopstick 1 is occupied by the P1. So again P5 also in the remaining state, in the thinking state. So in this case or in this scenario, only P1 and P3 can eat. And when these two are eating, P2, P4, and P5, these three processes, these three philosophers cannot eat the food. So if suppose similar kind of situation is always occur, then it may possible that P2, P4, and P5 it may go into the starvation. Or not only P2, P4, if suppose it may be possible that one of the philosophers it can be starved. So you need to design an algorithm so that such algorithm should work in such a way that there should be no philosopher to be starved, or philosopher should get the access chopstick and they can eat the food. You have to design such an algorithm. Okay, so in your book only this much code is provided. Perform weight operation on chopstick I. Suppose consider the value of I as a 1. So chopstick 1, perform the operation weight. Then perform weight operation I plus 1, that is on chopstick 2. And here mod 5, because here considering the 5 chopsticks or 5 count, and if the both operation perform, it can perform eating. Then after that, if suppose eating is finished, then he can perform signal operation first on the chopstick I, and then chopstick perform the signal operation that on chopstick I plus 1, and after that it will go into the think state. Okay, so this much code is only present in the textbooks, but I think it is not sufficient for the understanding. Okay, for the understanding, I have some other code. So I would like to share here. This is for the understanding. Okay, you can better understand from this code. So similar kind of code that is converted here, or it is implemented same. So this is the first try. Okay, this code is nothing but the first try that is provided here. Only thing is that here count is considered as the 5. Here count is not considered. So similar kind of the count is also considered as the 5. Has defined and 5, and consider and taking the fork that is nothing but chopstick has 1 2 3 4 and 5. Okay, by mistake it is 1, so it is a 1 2 3 4 5. So here the case is for the philosopher function, taking the philosopher function and passing the philosopher count, whether it is the first philosopher, second, third, or fourth. That is represented as the sorry, this count is the, you can consider the chopstick. Okay, for the philosopher it is the count for the chopstick first, second, and third, like that. So for the first, so if suppose any philosopher enter, then definitely he first in the think state for some time. Then when he feel hungry, then it will call the function take fork. You can consider here as the chopstick function. As mentioned here, performing weight operation on chopstick, you can consider here as the take fork. That is taking a chopstick. Then second function, that is the again take fork, that is the taking the chopstick second, and after occupying both chopstick, both fork, it is perform eat operation. After eating, it will put down the chopstick I as well as I plus 1. So this is the first try, or this is the first solution that is provided for the dining philosopher problem. But there is a one possibility. Suppose if P1 and P3 always get the chopstick or always given the priority, that I have already discussed. Suppose only P1 and P3, these two processes are always getting this chopstick. Then it may possible that P2, P4 and P5, it may get star. It may get star. So this is not as per our expectation. Our expectation is that no process should be star, no philosopher should be star. All philosophers should able to eat the food. But so this particular algorithm, it is not satisfy our requirement. So some modification is provided, and a second, and also one more condition is that if suppose all philosophers decide to pick up their left foot or left chopstick at the same time. What happened here? If suppose all philosophers they are thinking for the first for some time, and after that all of them feel hungry, and after that, in that case, the is left, he will wait. Similarly, P5 also finds that left busy, he will go for the meeting, and so on, and so on. So it may possible that It may possible that the deadlock, it could be occur.
Hello, sir.
So
He- Hello, sir. Sorry for interruption,
hello.
but your voice is too breaking.
What- okay, okay. Is it audible now?
Yeah, sir.
Is it still breaking?
Now it is.
Now it is okay. 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 So condition is that second possibility is that the process it may go for the possible it is the possible stagnation. It may be due to a deadlock. How the deadlock could be occur? If suppose P1 occupy first chopstick and then it try to occupy second chopstick, but this chopstick is already occupied by P2. Why? I have I told the condition that all P1, P2, P3, P4 and P5 they suddenly at the same time feel hungry and they all try to occupy the chopstick. Then in that case, P1 first will occupy first chopstick, P2 it will occupy second chopstick because it is on right side, P3 occupied third chopstick, P4 fourth and P5 fifth chopstick. Now when P1 tries to occupy second chopstick which is already occupied by P2, then P1 it will go in the wait. It will wait for the second chopstick. Similarly, when the P2 just a second. Similarly, when P2 tries to occupy third chopstick, which is on his left, then it is already occupied by P3. So that's why P2 also will go into the waiting state. Likewise, P3, P4, and P5 all will go into the waiting state. So these all are go into the waiting state, and since either it is waiting state or they could have blocked himself, then in that case the condition is become the deadlock because no one is there for awake to other one. All are in the block condition or waiting state. So this could lead to a deadlock. So these two problems that may be happen by referring this particular algorithm. So okay, I think you know already deadlock. Okay, you can see all the vehicles they are become a deadlock. No one can go in either direction. Okay, in the center तुम्ही बघू शकता की सगळे व्हेरिकल एकला ब्लॉक करू नये एकही व्हेकल एकमेकाच्या पुढे जाऊ शकणार नाही. So this condition is called as the deadlock. Similar concept we can implement for the program. Each program is waiting for an event that another process can cause. That means program is waiting or program is blocking and waiting for the wake up call from the other process, but all other processes are in the blocking state. So no process is there for the wake up to other process. So the condition become a deadlock condition. So that's why some modification is performed in the algorithm, and the this second try is presented. So in this second try, you can see here the philosopher, which is in sync, which all are initially sync state. Then they will call take 4, that is collecting their right chopstick, and then afterwards it will check if the left chopstick is available or not. So that's why it is using the if condition. If chopstick is available, then only it is going to perform take 4 function to occupy the left chopstick, and then it can perform the eat. If it is not available, then it is going to perform put 4. It is going to perform put 4 of I. What is the right chopstick? Now suppose, okay, imagine that all philosophers start run simultaneously. Then again it may be possible that all philosophers they are taking the chopstick and putting it down continuously. Okay, that means all five start their working at the same time. They are picking their first chopstick at the right side, and they are accessing for the second chopstick, that is their left side. They are picking available, and they find that not available. Again, they are going to take one chopstick and go for blocking state for certain amount of time. Again, after certain amount of time, again they come at the same time and perform the question. This is happens again. It is a positive process. Okay. Again, they do the same. The better alternative, philosophers wait for random amount of time before making the stop. त्याच्यासाठी एक यायची पॉसिबिलिटी फार कमी आहे. This could be a better solution or better alternative for the deadlock problem. Okay, so in this case, if we implement this solution, then it may be possible that the system can run better. And the same thing or such scheme is used in the Ethernet. Okay, in the Ethernet, the second try scheme is used. Now you can also provide the solution by using the mutex. You can also provide the solution by using the mutex. What you can do, one mutex variable you can use and perform the wait operation before taking the chopstick. Before taking the chopstick, perform the wait operation, and after that, performing the full function, putting the chopstick, it will perform again the signal, so other can take the chopstick. But here, the performance issue is a major problem because only one process can enter into this chopstick, or only one philosopher can take the chopstick. All other four have to wait. That is the problem. Okay, so it is not this is preventing the deadlock. Okay, no doubt, it is preventing the critical section, it is protecting the critical section as well as preventing the deadlock. But performance issue is there. Only one process or only one philosopher can work at a time. So this is not a feasible form from performance perspective. From the performance perspective, this is not the solution. So by using semaphore, this another solution is provided. So using a semaphore, in the semaphore, three variables or three states they are using, that is hungry state, eating state, and thinking state. A philosopher can only state if neither, this is most important, it can move to the eating state if neither neighbor is eating. Here in the mutex, you can see here, before checking the status of the neighbor, it is directly providing the waiting state. Directly it is locking. But here it is providing the locking if only neither neighbor is eating. Okay, that is the main thing. So consider the philosopher. Okay, here four functions is given: philosopher, take four, put four, can take. So first focus on the philosopher. So in the philosopher, you can see first function is the think function, where all the philosophers are thinking state. Then when they are feeling hungry, then they will call the function take four, take toxic. Then in the take four, first perform the lock variable or local variable. Then the status hungry, you will see the status was thinking. You will see the status was think. Now it is updating the status hungry, and then it will call the function taste. In the taste function, downside, in the taste function, it takes that the state of I is hungry. Definitely, it is previous state. The state of I is hungry, and state of less is not equal to getting. Suppose it is first person, again it says the state of I not equal. Again it is true, then only it is going to say the same as which. Then it is called
Hello, hello, sir.
hello. Yes,
Sorry for interruption
yes.
again, but y- your voice is not clear. There is some noise from your side.
Yeah, sir, it is simultaneously breaking. Not clear from your background.
And sir, please once again repeat first try and second try.
Okay, okay. Okay, is it clear now? Can you listen now?
Yeah, sir.
Okay. Okay, so in the first try, what happened? All the philosophers are in the think state. All are in the think state. If suppose they are feeling hungry, then they are going to take first chopstick by calling the function take fork. They are collecting take four of I, that is their right chopstick. After that, again they are calling the function take four for the second chopstick, that is at their left side. If both chopsticks available, then they are going to perform eating function, or they are going to perform eat. After eating, they will put down the first chopsticks, that is at the right side, and then left chopstick by I plus 1, indicating I plus 1. Okay, that is the first try. But what could be the problem here? The problem is, it is possible that if the all philosopher that decide to pick up their left chopstick at the same time, what happen? If suppose all philosopher they try to pick their left chopstick at the same time, then there could be a possibility of starvation. How? Suppose for the philosopher P1, philosopher P1, P2, P4, P5 all agree and on first occupying their chop, and they will get it. Okay. All of P1 will get the first chopstick, right side P2, right side second, so it will get second chopstick, P3 third, P4 fourth, and P5 fifth chopstick. All of them you will get their right chopstick. Now when all of them trying to take the left chopstick, that means for the P1 it will try for the second chopstick, P2 it is try for third chopstick, then P1 when it will try for the second chopstick, it is already occupied by P2. Similarly, for P2, if you try to access the third chopstick, it is already occupied by P3. Likewise, for P4, P5 also, similar kind of situation will be there. So this could be a go to the deadlock. This situation can be go into the deadlock. No any process can take the chopstick, and the condition of deadlock could be occur when the all philosopher they are trying to access their left chopstick at the same time. Okay, so this condition can be occur. Second thing, second condition, okay, similar kind. If P1 and P3 they are getting the access, then it may possible that P2, P4 and P5 they cannot get the access. And suppose this happen all the time. This happen all the time. That means only P1 and P3 they are continuously getting the access to their chopsticks. Then in that case, P2, P4 and P5 they may starve. They may starve. So the starvation and deadlock. These are the two problems when we are trying by using the first try algorithm. Okay, this is our first algorithm. So this algorithm it may produce the problem of starvation as well as deadlock. So that's why they have proposed the second try in which when any philosopher accessing to their left chopstick, it will first check the availability. In the if loop, it will check if it is available. If it is available, then only it is going to take it. Otherwise, it will put down his right chopstick also. Okay, if it is available, then he is going to take it and perform the function eat. If the left chopstick is not available, then he also put down the right chopstick also. That is the condition. Okay, but there could be a problem when all the philosopher they are trying for the same. For example, if P1, P2, P3, P4 all are taking their right chopsticks, and for the left they are checking this if condition at the same time. If all they are checking the same condition, then definitely nobody will get the access to their left chopsticks, and they are going to put down their right chopstick also. And after some time again they are coming at the same time, and again the same scenario could be happen. So again there may be a possibility of deadlock. So to solve this one, the better alternative is the philosopher should wait for the random amount of time before taking the right chopstick. That is calling the function take work of I. Resolution, philosopher should wait for a random amount of time. Now this random time, it is not same for the all philosopher. Okay, it will not be a same. It may be a different. Rarely it may be the same, but most of the cases this will be a different. So this is provided the solution, and that's why this solution is used in the Ethernet. Okay, so here we are providing random amount of time, and we can solve the problem. Now similar kind of solution we can provide by using the mutex also. We can use the mutex variable, and we can perform the wait and signal operation on the mutex. Before taking any chopsticks, philosopher will perform wait operation. Then it will chopstick right and left, perform eating, and then it will perform the put operation. That is it is put the chopstick and then perform the signal operation. Definitely this solution will give you this solution can protect the critical section as well as it can prevent the deadlock. But there is a issue of performance because only one philosopher can eat at a time. Only one philosopher can eat at a time. All other philosophers should have to wait. So performance, it is the major issue in case of mutex. We have seen our example that if there is we are not using mutex, we can use there can two processes can enter into the system, or two philosophers can eat at the same time. But using the mutex, only one philosopher can eat at the same time. So this is not the feasible solution. Performance issue is major issue. So that's why the solution is provided uh, by using the semaphore. So in the semaphore, three states or three variables they are using. There is hungry, eating, and thinking. Philosopher, it may be in the three state: hungry, eating, and thinking. Second thing, the philosopher can move to the eating state if neither neighbor is eating. That is the most important situation, most important condition. Here, he is focusing on the neighbor. If eating is not performed by the neighbor, if neither neighbor is eating, then only it will go into the eating state. Otherwise, it will in the thinking state. So go to the function. Four functions are there: philosopher, take fork, put fork, and taste. Four functions are there. So in that, first look at the philosopher function. In the philosopher, first is the think. All are thinking in their initial state. Then when it is hungry, take fork. Go to the take fork function. In the take fork function, first it will perform lock operation on mutex. After that, it will mark state as hungry, and it will call. Can you see my screen? Okay, because current is not there. Can you see my screen?
Yes, sir.
Yes or no? Yeah. Okay. So here in the test condition, it will check if the state is hungry. In the previous statement, we have said state is hungry, condition true. It will check if the state of left, it is eating, not eating. Condition is true, nobody is eating, left part is not eating. Again, to check right is eating or not. If it is not eating, then all condition become true, and it will set the state as eating. And then it will call up function. Up, or you can say it is a signal operation. I think screen is not visible now. Is it correct?
Yes, sir.
लाईट गेली त्यामुळे आता काय त्याला सोल्युशन नाही. ठीक आहे, हे ऑर्डर राहिलेलं पण आपण नेक्स्ट सेशनला घेऊया. Okay, give me attendance. A division, roll number 1.
Present.
2.
Present, sir.
3.
Present, sir.
4.
4 present, sir.
5. 6. 7.
Present, sir. 6.
Okay, 7. 8.
Present.
9.
Present, sir.
10.
Present, sir.
11.
Present, sir. 7. Present, sir.
12.
Present, sir.
13. 14. Speed up.
Present, sir. Present,
14.
13. Present, sir.
15.
14.
16.
Present.
17.
16 present, sir.
Okay, 17.
17 present.
18.
Present, sir.
19.
Present, sir.
20.
Present, sir.
21.
Present.
22,
Present, sir.
23,
Present, sir.
24,
Yes, sir.
25,
Present, sir.
26, 27, 28,
28. Present, sir.
29,
Yes, sir.
30,
Yes, sir.
31, 32,
Present, sir.
33,
Present, sir.
34,
Yes, sir.
35,
Yes, sir.
36,
Present, sir.
37,
Present, sir.
38,
Present, sir.
39,
Present, sir.
40,
Yes, sir.
41, 42,
Yes, sir.
43,
Present, sir.
44,
Present, sir.
45,
Present, sir.
47,
Yes, sir.
48,
46 present.
okay, 48,
Present, sir.
49,
Present, sir.
50, 51, 52, 53, 54,
Present.
55,
Present.
56,
Present.
57,
Present.
58,
Present.
59, 60, 61,
Present, sir.
62, 63,
Present, sir.
64,
64 present, sir.
65,
Present. 64
66,
present, sir. Present.
okay, 66, 67,
Present. Present.
8, 68, 69,
Present, sir.
70,
Present, sir.
okay,
27,
absent roll
sir.
number for A division, okay, for A division, 5, 7, 26, 31, 41, 50, 51, 52, 53, 59, 60, 62, 68.
Hello, sir. Roll number
51
5
present,
is
sir.
present.
5 present, 51 present,
26
okay,
present.
26 present. Finish. So roll number 7, 31, 41, 50, 52, 53, 59, 60, 62, 68. Absent roll number. Okay, B division, roll number 1,
Present, sir.
2,
Present, sir.
3, 3, 4,
Present.
5, 6,
Present, sir.
7, 8,
Present, sir.
9, 10,
Present, sir.
11,
Present, sir.
12,
Present, sir.
13,
Present, sir.
14,
Present, sir.
15,
Present, sir.
16,
Present, sir.
17,
16.
Present, sir.
17,
Present, sir.
18, 19, 20,
Present.
21,
Yes, sir.
22,
Present, sir.
Present, sir.
23,
Present, sir.
24,
Present, sir.
25,
Present, sir.
26,
Present, sir.
27,
Present, sir.
28, 29, 30,
Present, sir.
31, 31, 32, 33, 34, 35,
Present, sir.
36, 37,
Present, sir.
38, 38, 39,
Sir, 39
40,
present.
okay, 40, 41,
Present, sir.
कोणता अविनाश गुण 40 का 41?
For 40, sir.
हाँ 40, 41, 42,
Present, sir.
43, 44,
Present.
45,
Yes, sir.
46,
Yes, sir.
47,
Yes, sir.
48, 49,
Present, sir.
50,
Present, sir.
51,
Present, sir.
52, 53, 54, 55,
Present, sir.
56, 57, 58,
Present, sir.
59,
Present, sir.
60,
Present.
61,
Yes, sir.
62, 63, 64, 65, 66, okay, 67, 68, 69, 70, 71, 72,
Present, sir.
73, 74,
प्रेजेंट हो गया लेफ्ट से लेफ्ट
okay, 75,
प्रेजेंट
76,
Present, sir.
77, 78, 79.
Present.
Okay, absent number for B division 3, 5, 7, 9, 19, 9 present. 19, 28, 29, 31, 32, 33, 34, 36, 38, 41, 43, 48, 52, 53, 54, 56, 57, 62, 63, 64, 65, 67, 68, 69, 70, 73, 77, 78. Anybody? You can leave the session.